So let's go ahead and consider how our quantifiers distribute over and or. So it turns out that it's not as straightforward as distributing not over ands and ors, etc. So this theorem is going to consist of 4 different parts. So our theorem is as follows. So for the very first part, our universal quantifier right here distributes over ands. So if I have for all x, p of x and q of x, I can distribute that for all of x over to the p, and I can distribute it over to the q as well. And by order of operations, I know that I have to evaluate this expression, see if it's true or not, and evaluate this expression, see if it's true or not, to figure out the truth value of this right-hand side right over here. So I can distribute this universal quantifier over ands. The second part is that my existential quantifier distributes over ors. So here again, if I have there exists an x such that p of x or q of x, I can take that existential quantifier and distribute it over each one of them. I distribute it onto the p, I distribute it onto the q over here. The thing that makes it interesting is that this is the only way that it works. So I'm going to do this in a different color because these are going to be not logically equivalent. I cannot distribute my universal quantifier over ors. I cannot do this. They're not logically equivalent. And similarly, these two are not logically equivalent. I cannot take my existential quantifier and distribute it over an and or a conjunctive right here. So these are 4 claims right here, and they are all proved in Rosen. I am not going to prove them all for sake of time, but let's go ahead and just look at this very last one and see why these two are not logically equivalent right here. So remember from our definition of logical equivalence, the left-hand side and the right-hand side, for them to be logically equivalent, have to be true no matter what my domain is and no matter what my propositional functions right here stand for. So for part D, if I were to consider the following propositional functions. So P is going to be my propositional function x is 1, Q is going to be my propositional function x is equal to 2, and the domain that I'm going to consider is going to be R over here. So let's go ahead and look at this right-hand side over here. So if I were to look at there exists x such that P of x on this domain of all real numbers, well, does there exist an x such that x equals 1? Well, yeah, this thing is logically equivalent to there exists an x such that x equals 1. And definitely that is true. Indeed, all I have to do is let x equals 1, and I have found an example of the existence of some value in my domain that makes this true. So yes, that one is true. And then I can consider there exists an x such that q of x. Well, yeah, again, this thing asks me, is there a real number that's equal to 2? Well, definitely. All I have to do is let x equals 2. And so here again, the scoping is important because even though I've written an x over here and I've written an x over here, the scope of this x and the scope of that x are different. So when considering that statement, I can find an example with x equals 1, and when considering this statement in isolation, I can consider x equals 2. So therefore, what I have shown is that there exists x such that p of x, and there exists x such that q of x. That thing is going to be true and true, right? True and true. So this thing is true over here. However, if I were to consider the left-hand side of my d over here, let's go ahead and write down this expression and see what it translates to. So if I were to write down that guy, well, if I were to unwrap the definition of p of x and q of x, this thing is logically equivalent to saying there exists an x such that x equals 1 and x equals 2. And you can immediately see that there is no real number that is both simultaneously equal to 1 and equal to 2. So therefore, this thing is false. So I've shown that for a particular propositional function in a particular domain, my left-hand side is false and my right-hand side is true. Therefore, these two logical expressions are not logically equivalent over here. So to summarize, with my distribution, existential quantifiers distribute over ors, universal quantifiers distribute over ands, but not the other way around.